So the question had to do with the role of chaos. And its relationship to what I was speaking about this morning, the potential role for complex systems models or system science models within the public health sphere. Okay, so I'll address that question in several parts, and Elizabeth can jump in at any point if she's interested. So first of all, I should note that you'll find within the instructors in this room will sometimes, reflecting our different backgrounds and kind of predispositions, will sometimes use different words for similar things. I tend to fall into saying system science, which is a technique, which is a term that was particularly promoted and popularized by NIH in the health context, although it's not unique by any means to that community. Here in Michigan, there's a lot of discussion of complex systems as the terminology. And regardless of how you parse those, but I think particularly from a complex systems perspective, there's actually several areas beyond modeling that fall within the complex systems rubric, okay? Within the complex systems, dynamic modeling is a big part of it. Dynamical systems theory is another component. Theory of chaos and chaotic dynamics is an active area of research that dates back to the late 60s and Doyle Farmer's work and in the Santa Cruz Collective, et cetera. Santa Fe Institute has been involved in that as well. I do a lot of work these days with methods known as convergent cross-mapping for detection of causal relationships within temporal data. That's another complex systems method that we find very informing for our dynamic models. But all of this is to say that what we're concentrating in this course, these models for insight within public health to what's going on, where to intervene, where to prioritize data collection, et cetera. Those are just a subset of complex systems methods. And chaotic dynamics and chaos theory have to do with this very interesting phenomenon, which I've worked some, where you have nonlinear systems, there is often a phenomenon by which there's sort of a butterfly effect. Small differences at one point in time can be magnified into very large differences in outcome over time. And there's some mathematical reasons for this. And one of the consequences of this is that we can get behavior over time that would appear to have elements of randomness, but it's actually got hidden order behind it. There's hidden order underlying it. And within the sphere of physical systems, these chaotic systems are notable. And they include everything from planetary motion to drops coming out of water faucets to behavior of certain electrical systems, et cetera. Within the health sphere, I will tell you that while I've done work with chaotic systems and so on, I have yet to come across an absolutely compelling public health level characterization where chaotic dynamics seem to me to be at the heart of what requires explication and where they're a needed part of reasoning about the system. I think it's fascinating to me mathematically. It's really interesting for certain physical systems, and we certainly will sometimes build models using these same tools of these systems. So Lorentz attractor, for example, illustrating chaotic dynamics. But I have yet to find it a key tool within the public health sphere. And I don't know, Elizabeth, if you've found yourself sort of needing recourse to the chaotic systems literature at all. But
I mean, I'm in complex systems at Michigan, and I can say that I think that there's a lot more to that field than the stuff that we're talking about today. I think that for public health applications, the biggest payoffs of this area have not been around chaos as much as finding a powerful framework in which to explore feedbacks at different levels, and it's one individual over time, between people, between individuals and groups, and so in the same way, I haven't found a clear application.
yeah, and one thing I will say about this is that the constructs used, the formal approaches and the visualization tools and concepts used for approaching investigations in chaos also are useful, actually, in my experience, in my day-to-day practice within the public health sphere. So we will, again, I don't want to lose people in this right now, but we will create state space or phase state portraits of, incipient outbreaks, and we will examine data within what are called embedded shadow manifolds, and those are really useful things. They tend to be very advanced things that most practitioners of these methods don't tend to use, although one could say that they could enhance their potential by using them. But I would say that at the least, that there is useful stuff related to complex, to chaotic dynamics, but it is not part of the core set of material that we need to communicate as part of this course. And if someone in this course were to go in a deep dive in chaotic dynamic side, I think you would find intellectually intriguing material, but I remain wholly unconvinced that you would secure too much in the way of public health insight from that. And I could be faulted, I could be wronged in that, and I am eager to learn from someone who has done more investigation. But from knowing quite a bit about that literature and respecting it, I don't think it's one that brings a lot to the table when it comes to public health application. Okay. Other questions? Great stuff, that question. Other questions? Okay. Good. We'll be eating lunch together, and so there'll be lots of opportunities for further informal questioning as well. Great. So I'm going to stop that recording.